left, and then suddenly, okay, you say you have to make a correction again to the right this time. But again, when you make an overcorrection to the right, and this time it's going to be even a bigger correction to the right. You go even more to the right this time, and then you make a bigger correction to the left again, and suddenly you found yourself in the drain. That's what we say when we say that the system is unstable. The response is unbounded. It's getting bigger and bigger and bigger. For example, here. Here this is. Why is it everything is there? What's going on? But the input, okay, imagine this is the system. The input must be bounded first. Of course, when the input is unbounded, then we can expect that the output is unbounded as well. So this is some of the typical input that might be imposed on a system. It can be an impulse, a step, and some traction input. The first two examples here, this is a stable system, and oscillation does not mean that the system is unstable. It is just oscillation, increasing and then decreasing back, also still a characteristic of a stable system. Only when the response, the output is getting bigger and bigger and bigger and bigger and suddenly very big. That is what we mean by the system become unstable. So what exactly made the system become unstable? What is it? What is it that made the system become unstable? I forget about that. Let's take a look at this example 3 and example 3.1 and example 3.2. So we have this system. What's going on? What's going on with my screen? What's going on with my screen today? So what's going on with my screen? What the hell?
Not sure, Doctor.
Someone chanting your screen. It's vandalism. Yeah, I know that. What the hell is going on with my screen today? Okay, never mind. So okay, so we were discussing what make the system become stable or unstable, mathematically speaking. So why my computer is so slow today? Probably it's about time for me to get a new one. Yes. All right. So look at example 3.1. So he says here, obtain the time response of the system shown below for a unit step input. Determine whether the system is stable or not. So when the system is subjected to a unit step input, does this system stable or not? This is very simple question. By the way, I don't play games. I'm just an old man already. By the way, today I'm back in my office, so I can write something on the board today. But what the hell is going on with my screen today? I don't know. There's something.
Aduh, wei. Tak boleh jadi. Aduh. Buat aku tekan ni.
Oh.
Aduh, jatuh. Sorry. Aku nak set ni.
Asal kacau live tu.
Alright, so that's example one. We have example one. So the system is 1 divided by s plus 1. So the output is u of s multiplied by that. But since we have this unit step input is in Laplace transformation format, is just 1 over s. Okay, so then T. So now this is the response to a unit step input, and then if you draw the function there, it's just exponential function. See, the critical here is the minus sign here, e raised to the power of negative t. So that is going to be, as t approach infinity, that's going to approach 0. So your final value is equal to 1. Yeah. Why don't you just everybody just sing, and then we can have some fun here. So we say that this system is now is stable. Stable meaning that the output is bounded. It does not get very large. It doesn't get infinitely large. So this is a stable system. For a unit step input, which is a bounded input, and then our output is some exponential function that finally approach the value of 1. So we say that this is a stable system. And of course, as you can tell already, the second example by default is going to be unstable. Otherwise, why we are doing this? Example 3.2. Now, obtain the time response of the system shown below for a unit step input. I'm just going to write example 2. So 1 of s is equal to s1 s. This is minus. Oh, sorry. Let's go to the whiteboard. Okay. So that's example 2. And then for a unit step input, then you perform the partial fraction. Then you have that. So you start at what? Start at 0. And then if you draw the response, okay. See, because this is e raised to the power of positive t, as t approach infinity, so that is going to be infinitely large compared to -1. So it's going to increase. So this is what we mean by unstable system. So what exactly makes the system unstable mathematically? So you can see that the system becomes unstable if only one of the term approach infinity depends on the sign of the roots of the denominator here. So if you have a positive root, then the system is going to be unstable. Here you have a negative root, -1, but in the second example, so the root is +1. The roots of the denominator of your transfer function. So if you have one positive root, then your system will become unstable. So you can generalize that by stating that okay, so stating here that where is it? Oh, okay, the discussion will come in later. So the sign of the roots of the transfer function will determine whether the system becomes stable or unstable. So we will be looking for a positive root. If there exists a positive root of the denominator, and then we can safely say that the system becomes unstable. So in general, we can discuss in general term what stability means. Now, if we look at the closed loop system, we're going to have this forward transfer function gh of s and the feedback transfer function h of s. So when we obtain the overall transfer function, we have this g divided by 1 plus gh. So the equation 1 plus gh is known as the characteristic equation. See, the denominator of the transfer function equal to 0 is known as the characteristic equation. This equation will characterize whether the system is stable or not. So the roots of this characteristic equation will determine whether the system is stable or not. If there exists one positive root, then the system becomes unstable. Only one is enough to make the system become unstable. We want all the roots to become negative. For example, here, if you write the equation in zero pole format, so this is known as zero pole format. Z plus S, S plus Z1, S plus Z2, there is a numerator. The numerator will not determine whether the system is stable or not. Only the denominator of the transfer function that will determine whether the system is stable or not. If there exists one positive root, then you can safely say that the system is now become unstable. Only one term that will go to infinity is enough to make the system become unstable. But sometimes the roots are complex. It is not just a distinct real number. When the roots are complex number, then we are looking at the real part of the roots. If there exists a positive part of the roots, then we say that the system is unstable. So we can see the region for stable system and the region for unstable system. Where is it? There. On complex plane, So if you plot all the roots of the characteristic equation, okay, but by the way, what is the roots of an equation? For example, a quadratic equation, ax squared plus bx plus c equals 0. So the roots are the value of x that will make the equation equal 0. If you have a quadratic system, then you're going to have 2 roots. If you have a third order polynomial, then you're going to have 3 roots. For a stable system, you want all roots to be on the left hand side of the imaginary axis. You're going to have some real roots on the real axis, and you're going to have some complex conjugate roots. As long as the roots lies on the left of imaginary axis, then we say that the system is stable. We need all roots to be on the left hand side of the imaginary axis. Sometimes the root, we say the root, sometimes we say it's the pole. Sometimes we use the term pole and roots interchangeably. See, all poles of the closed loop transfer function must have a negative real value, meaning that all poles, sometimes people use poles interchangeably with the roots. The control engineering people like to use the word poles. The mathematician use the word roots. As long as all poles lies on the left of imaginary axis, then we say the system is stable. So this is called a complex plane, an S-plane. If one root lies on the right of imaginary axis, on the S-plane here, and we say that the system is unstable. One root lies on the imaginary axis on the S-plane, then we say that the system is stable. All poles, for a stable system, all poles must be on the left of the plane. This is called the S-plane of a complex number. I can still remember the joke my professor, my lecturer, when he talked about this stability of closed loop system, probably 35 years ago, I think. I still remember the joke until today. Now I'm passing the joke to you, so that in the future you can tell your children about this joke. So he said that one day he was flying he was flying in a plane. See, you can see where the joke is going already, right? So this is the plane, the complex plane, imaginary axis, a real axis. It must be to the left of the imaginary axis. And then he said he was flying in a plane over an Atlantic Ocean, and suddenly the plane hit a turbulence, so it becomes slightly unstable. And then he said that, okay, the captain make an announcement. Hello, this is your captain speaking. All poles, please. Okay, we are experiencing some turbulence that making our plane unstable. So to stabilize the plane, please all poles move to the left of the plane. Did you get the joke? No. See, the Polish people, we call that pole. So the captain wants the poles to move. All the Polish people move to the left of the plane so that the plane becomes stable. Forget about it. You never get my joke anyway. All right. Okay. So we want all the poles to be on the left of the imaginary axis. Now let's take a look at this. Example 3.3. Determine the stability of the system with characteristic equation given below. So this is the characteristic equation. Characteristic equation is the denominator of the overall transfer function. Only the denominator of the overall transfer function will determine whether the system is stable or not. All you have to do is find the roots. If one of the roots are positive or has positive real part, then we know that the system is unstable. So this is a third order. You're going to have 3 roots. Let me go back to my whiteboard. Okay. So, okay, this is now a third order polynomial. So we can factor one of the roots at -2, and then since this is a third order, then we're going to have 3 roots. One is the real root, which is -2, and the other one is -1 plus and minus j. So we see that. So this is all the 3 roots. The one that I marked by x. So those are the 3 roots. So or the poles. So since the roots or the poles lie on the left of imaginary axis, and then we see that the system is stable. So a third order system is going to have 3 poles or 3 roots. As long as all the roots lies on the left hand side of the imaginary axis, then we say that the system is stable. Let's go on to the next question. And then you need to do this for every single system. So finding the roots of higher order polynomial, it is not that easy. Even a third order polynomial is not easy for you to find the roots unless you have a very good calculator. Then you can just plug in the equation and the calculator will give you the roots for you. There's always a trick for that. Now let's take a look at next question. (2.4). Right. For a marginally stable open loop system below, determine the stability of the closed loop system if the proportional controller gain Kp is equal to 24 is used. Now, it is given that this is an open loop system. It says that open loop system is marginally stable. Marginally stable because one of the roots is 0. See, your roots are -1, -2, which is on the left of imaginary axis, but one of the root is 0, is exactly on imaginary axis. So that is why this is a marginally stable open loop system. And smart Alex come in here and say, okay, since this is a marginally stable system, let us use a proportional controller gain, KP, turn this into a closed loop system and see whether the system is stable or not. Originally, the system is marginally stable. Now we are going to turn this into a closed loop system with a proportional controller gain 24 and see whether the system is stable or not. Let me go to my whiteboard. Now this is now a closed loop system with a proportional controller gain 24 selected for us, and all you have to do is obtain the characteristic equation and then obtain the roots to show whether the system is stable or not. All you have to do is obtain the characteristic equation. So that is your characteristic equation. 1 plus GH equals 0 is your characteristic equation. The denominator of the transfer function. All right. So now you want to find the roots of this equation. Okay, so now you obtain the characteristic equation, which is 1 plus GH equals 0. And it turns out it is a third order polynomial. Plus and minus 2.4J, that's correct. JOI, sometimes some people use J, some people use I for imaginary part of the equation. So normally I use J. J or I. You can use either J or I. And then there are going to be three roots. One real roots at -4, and then there's two more roots at 1/2 plus and minus 2.4j. And then you see that there are two roots lie on the right hand side of the imaginary axis, and then we see that this system is now become unstable. Because we have these two roots on the right hand side of the imaginary axis. So all you have to do to know whether the system is stable or not is just determine the roots of the characteristic equation. If there is one positive root, or you have a positive real part of imaginary roots, then you know that the system is unstable. Do you have any question? Why 0? That's 0. So the definition of characteristic equation is only then we can talk about the roots of the characteristic equation. So 1 plus GH equals 0 is known as the characteristic equation. The denominator, when we equate that to 0, if we don't equate that to 0, you won't be able to solve for the roots. It is like ax squared plus bx plus c, and then if you don't put equal 0 there, and then it is not an equation that you cannot solve for the roots. That is why we put 0 here. So the definition of this characteristic equation is the denominator of the transfer function equate that to 0. That is known as the characteristic equation. Any other question? Okay, so sometimes we wish that we can have a simpler method of determining whether the system is stable or not. If we are only interested whether the system is stable or not, we don't have to compute the exact root, the exact numerical values of the roots. There are some tests that we can use that we are going to discuss after this. But I think we take a break first. We take a break here. And then we'll come back for, what time is it? It's 4:40. Come back at 5 and we continue from there. Okay, I'll see you back here at 5, and then we discuss how we can determine the stability of the system without computing the exact value of the root. Isn't that working? Isn't that working, taking the denominator? What the hell is going on with my screen? All right, so come back here at 5 and then we continue our discussion. In the chat group. You see, I just had this feeling. I just have this feeling that one day, one of these days, when I ask you if you can hear my voice, type yes in the chat box, and then everybody is going to stay quiet. I just get that feeling. I know that one day is going to happen. All right, so there is some discussions going on in our chat group. Let me point out one of the most common mistake that the student will make when they want to get the characteristic equation or the overall transfer function. Even as I keep reminding you this, even I pointed out that this is a common mistake, some of you still going to do this. some of you still going to do this. So this is the common mistake. See? Now, this is the most common mistake that the students make. Even as I scream out on top of my lung, this is the mistake you're going to make. This is the mistake you're going to make. You're still making this mistake. This is not right. This is not right. You cannot do that. That is just freaking wrong. Even as I remind you, even as I draw this diagram, even as I cross it out using red marker, some of you still going to do that. Some of you. Not to mention the one that who never attend my class. No, that's not right. There. This is G divided by 1 plus GH. This is the overall transfer function. And the characteristic equation is the denominator. The denominator equal to 0, then you get the characteristic equation, not just this s plus 1, s plus 2 equals 0 equals 0. That's not characteristic equation. So don't do that mistake. No. You don't want to do that mistake. All right, so let us continue our discussion. It would be nice if we can determine whether the system is stable or not without having to compute the value, the numerical value of the roots. There is a test that you can conduct to know whether there exists a positive root or not. It is known as the Routh stability criterion. The Routh stability criterion is a method can determine the existence of positive pole. That's all we need to know, whether there exists positive pole or not. So the criteria is sufficient if we only wish to know whether the system is stable or not. But we will not know the exact behavior of the system. But never mind, it is a good test. All you have to do is obtain the characteristic equation and conduct the Routh table, construct the Routh table. So this is known as the Routh table. If the elements of the first column have the same sign, then we say that the system is stable. So how do you construct this Routh table? It's very small, whether you can see this or not. I have a bigger, probably mine is better. This is my notes. I wrote some notes. I post this on your e-learning so that those of you who do not attend my class will have some reference. I know the attendance is not full, but never mind, forget about it. So we want to conduct this Routh stability criterion, whether to see whether the system is stable or not. First, you obtain this characteristic equation, 1 plus GH equals 0, and then you obtain the characteristic equation in terms of polynomial. See, it can be a polynomial of order n, fourth order or fifth order equals 0. Then you fill in the Routh table. Okay, so the first two rows of the Routh table, so this is the Routh table. The first two rows is filled in using the coefficient of the polynomial. So you take, if the characteristic equation is nth order, then you're going to have n number of rows, starting from s to the power of n. and going down to 0. The first two rows, the blue coefficient here, you fill in the first two rows using the coefficient of the polynomial an, and then you jump an minus 2, you jump one coefficient an minus 4, and the second row fill in with the again the coefficient of the polynomial. You start with n minus 1, and then you jump 1, n minus 3, n minus 5, and so on and so on. So the first step is to fill in the first row with the coefficient of the polynomial, and then you fill up the rest of the elements in the table. So you want to know, you want to compute B1, B2, B3, B4, C1, C2, C3, and C4, and so on until you get to s to the power of 0. So what is the element B1, B2, C1, and C2? Okay, so here you need to realize the pattern. You need to realize the pattern. So B1 is -1. To compute B1, so you look two rows above you. So you take -1 divided by an minus 1 and multiply by the determinant of the two rows above you, above B1. So the determinant of an minus 1, an minus 2, an minus 3. Okay, so B2, again, to compute B2, the multiplier is the same. The multiplier for B1, B2, B3 is the same. It is always -1 divided by an minus 1. The multiplier of B is always -1 divided by an minus 1. The first column of the determinant is also the same for B1, B2, B3. The first column is always an minus 1, an minus 1. It doesn't change. You only change the second column. If you look here, the second column for B1 is an minus 2, an minus 3. The second column for B2 is, so this is B2. So you look one column to the right, which is an minus 4, an minus 5. So, and then that is how you compute B1 and B2 and B3. And similarly for C1 and C2, to compute C1 and C2, so you look two rows above. The multiplier is always the same. It's -1 over B1. Is the first element one row above you. The multiplier for C1 and C2 is the same. -1 divided by B1, -1 divided by B1. The first column of the determinant is also the same. So in this case, you look two rows above, an minus 1 B1, an minus 1 B1 is the same for C1 and C2, an minus 1 and B1. You only change the second column. The second column, you look one column to the right. So for C1, so you take an minus 3 and B2. And for C2, the second column of the determinant, you look one column to the right. So an minus 5, B3. So this is a pattern. Human always look for pattern. You look up to the night sky and suddenly see, okay, there's an Orion, there's Big Dipper, something like that. So if you can see the pattern here, then we are in business. You can now compute the rest of the coefficient, the rest of the elements in the table, and to test whether the system is stable or not, all you have to see is column 1, the first column. If the sign of the element of the first column are the same, and then you can say that the system is stable. The system is stable. Okay, so let's take a look at an example now. Okay? The system is stable when all elements in the first column of the truth table have the same sign. For example, all positive or negative. Now let's take a look at an example. Okay. What the hell? Example 3.5. Determine the stability of the system with characteristic equation. This is a fourth order polynomial. And then here we want to construct the truth table. Of course, I already constructed the truth table for you. It's not that one. But you need to see how this truth table is developed. Ah, okay, this is a step by step. What the hell is going on? Step 1, step 2. Forget about that. Okay, I'm going to my whiteboard. Let me double check whether it is the correct. S to the power 4, 5s cubed, 20, 40, and 50. Okay, since this is a fourth order polynomial, so you're going to start your truth table at s to the power 4. So the first two rows, you fill in the first two rows using the coefficient of the polynomial. Okay, you start with 1, you jump to the next one, 20, and you jump to the next one, 50. So the first row, 1, 20, 50. 40s, yes. The second row, you start with the second coefficient, and you jump to the next one, 40, and there's no more there, so there's just 0. So now you need to compute B1, B2, C1, C2, D1, and D2. This is B1. So that's B1. To compute B1, you look 2 rows above. So the multiplier is -1 divided by 5. Is the first element on the on a previous row, and the determinant, you take the first column is just 1, 5, and then the second column you go one column to the left, 20 and 40, and then you can evaluate that. that will give you 12. So for B2, the multiplier is the same. The first column is the same, 1, 5. And you just change the second column, 5 and 0, 50 and 0. And then you can evaluate that. So that's going to be 50. Here, so B is equal to 12. B is equal to 50. That's it. Okay, so you continue. You can continue from there. You can now compute C1 and C2. C1 negative 1 over 12 plus 12 14. $230 over 12. And then you do the same for D1 and you get 50. So 0. Okay, so that's how you fill in the roof table. This is and then to determine whether the system is stable or not, all you have to do is just look for elements in the first column. So in the first column, you have 1, 5, 12, 230 over 12, and 50. So all positive there. If they have the same sign, all positive, then you say that the system is stable. All elements in the first column are positive. Therefore, the system is stable. See, all the elements in the first column are positive, then you say that the system is stable. Do you have any question? Why we don't need C2? All right. If it make you feel any better, then you can compute C2. C2 equals 0. You can verify that C2 is equal to 0. See, because the second column here, there's no more elements there in the third column, so you just 0, 0. So finally, you get C2 is equal to 0. Any other question? Well, that is how you develop the roof table. Okay. Now, example 3.6. Determine the stability of the closed loop system shown below. So this is where you are going to make a mistake on your test. You say, okay, this is easy. I can do this. All you have to do is fill in the root table using the coefficient of the polynomial, suddenly you fill in with just the denominator of that quotient, then that's not right. So you need to obtain the characteristic equation, then only then you can build your root table. Do I have that? Okay, so the step-by-step description of how you to fill in the root table is described in my notes, in my handwritten notes. Okay. There, everything is there. You can go through that. And then you fill in the element and look for the first column. Okay, so therefore the system is stable. So these are the elements in the first column. All right, so the first time, of course, we need to do into detail. After this, you just fill in the root table very quickly. Okay, now this is an example 3.6. A typical example, a typical question in your exam. In the process of you too eager to construct the root table, you just take s to the power of s cubed plus s squared plus 2s equals 0, and then you go on from there. No, don't do that mistake. First, obtain the characteristic equation, which is 1 plus gh equals 0, and then construct your root table. Okay? Fill in the coefficient from the characteristic equation. So this is a third order polynomial. So you're going to start at s to the power of 3. The first row, you fill in with the coefficient 1 and 2. And the second row, you start at the second coefficient, and then you jump 1, and you get, so 124. 1, 2, and 124. And then you can now compute the rest of the elements in the table. And then to see whether the system is stable or not, you look in the first column. You start with 1, 1, negative 22, negative 24, 1, positive 1, negative 22, positive 24. See, you have a sign change there. If see all the elements in the first column do not possess the same sign, then the system is unstable. The number of sign changes will tell you the number of positive roots. Here, positive, positive, negative, there's one sign change, and negative to positive, there's two sign changes. Therefore, this indicates that you're going to have two positive roots. There's a question in the chat box. Question will ask for root method. Is it, or is there any criteria? Most of the time, the question will not ask you which method that you should use. The question will ask, determine the stability of the system. That's it. And then it's up to you whether you want to find the exact root or the root table, unless the question specifically says that use the root criterion to determine whether the system is stable or not, then you have to develop the root table. As some of you who possess some calculator that can compute the roots, you don't want to learn how to construct the root table. I got that, I understand that, but sometimes the question will specify for you to construct the root table. The last variable I get 0, is it considered stable? If you have 0, then the system is marginally stable. See, if you have positive, 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 and one element is 0, then that indicates that the system is marginally stable. One of the roots lie exactly on the imaginary axis if you have 0 in the first column. I hope I answered that question. So here you have two sign changes. So that How to spell what? Unstable. How to spell it? Spell what? If all zero, if all zero, then you don't have a system. You have nothing. Everything is zero. It's like, no, you're not going to get all zero. All zero meaning that you don't have a characteristic equation. All zero meaning that 0s cubed plus 0s squared plus 0s plus 0 equals 0, and you have what we call a trivial case. We are not interested in a trivial case. See, 0s cubed plus 0s squared plus 0s plus 0 equals 0. What the hell is that? It's so trivial. Is that there is a trivial system? It means that you don't have a system to control. Where was I? Okay, here I was talking about the number of sign changes. You have two sign changes, meaning that you're going to have two positive roots. So for this equation, so I have determined the roots. So the roots are -3, and there's two positive root here. It is a complex number. It is a complex root, but the real part here is positive. So the number of sign changes in the first column indicate the number of positive roots. What else do we have? See? It is not difficult to develop the Ruth table, but just when you think that you have everything, see, life will always 3.7. This is 3.6. We are done. We are done with 3.6, right? This is 3.6. Okay, 3.7. Okay, 3.7. is done. So it looks like it is not that difficult to develop the Ruth table. But just when you think, just when you think that you know how to answer the questions, most of the time we are not that lucky. There's always something lurking behind us that sometimes determine our luck, whether we can do it or not. See, what happened if one, okay, what happened if one of the element in the first column is 0? Then you cannot proceed because the multiplier now become -1 divided by 0. Or in case this example 3.7 here. See, when you fill in the first two rows and then you compute the first element of the third row, you get 0 there. See, you cannot proceed to the rest of the rows because the next multiplier will be -1 divided by 0. You cannot proceed. So if there exists a 0 in the first element, for you to proceed, and you need to replace that with a positive small number. You can see here that B1 is going to be 0. So the next row you cannot compute because the multiplier is -1 over 0. And then you replace B1 with some small positive number, then you can fill the rest of the table. So now B1 is 0, but if you put 0 there, you cannot proceed with the computation of the rest of the element. So we replace 0 with a small positive element epsilon, so that you can now proceed computing the rest of the element. So so the multiplier of C1 is no longer 1 over 0, it is negative 1 over epsilon, and then you can now compute the rest of the element. And then again, since this is a negative, there's one negative element in the first column, then the system is unstable. Okay, the system is unstable. All right, so we are at the end of this Ruth table discussion. Let's take a look at the last example here. So this last example, instead of epsilon, can I use other? Normally, it is a standard symbol. Epsilon is a small positive number. Epsilon. You can use other symbol if you want, no problem. But mathematicians normally use epsilon to indicate a small positive number. All right. So now here, determine the range of k to ensure the closed loop system is stable. So we want to know the value, the range of k that you can have so that the system is stable. You cannot, when design a controller, you cannot have a very large value of proportional controller. So in this case, we want to know the maximum value of k that still make the system stable. So we can use the Ruth table to determine the value of k. Let's go to my notes. Okay, so you obtain the characteristic equation. Do not just get the denominator of g equals 0. That is incorrect. See, the first step is always to obtain the characteristic equation and then construct your Ruth table. Third order, and then you have this 130 in the first row, 13k in the second row, and then you proceed to compute the rest of the element. For a stable system, you want all the elements on the first column to be positive. So k must be greater than 0, and k cannot be greater than 390. If k is 390, then you're going to get, if k is greater than 390, then you're going to get a negative value for your B1. So for stability, you want your k to be greater than 0 and less than 390, or you can put that in an equality. So this is for stability. K must be between 0 and 390. Do you have any question? All right, so that's the end of today. So that's the end of today.